good.
I was talking about because I drew a picture of my math teacher in my notes one day.
It really sucks.
It was on the first day.
Really?
Yeah, he was just going to this and was like,
Didn't even realize it.
how does this do? And then like this one has like a solar distance on it. I don't know why. And then I wrote down like.
Is this gonna turn on? There we go. Okay. Forgive me in advance. I'm getting over a little bit of sinus infection, so if I'm going a little slower than normal, my apologies. We are in lecture 10. Hope everything's going on. Everybody enjoying the class so far? Yeah. Okay, good. Good. I really like teaching this class. It's a lot of fun. So I like teaching. There's an old joke. I teach for free. They pay me to go to meetings. That's a joke. Although actually not a very funny one. Okay. All right. Here, let me move this pointer over here. I'll make the screen bigger. Get the QR code up. Okay. I think we're up to date on homework grading, and I asked this before, but I assumed the 2x2 joint solution that went well. Good. We have our last Truss assignment today, which is due on Friday, and then I'm giving you a homework on Friday that is not due until Wednesday. Okay. So I'm giving you time on that Friday assignment. Okay. And it's mainly because Friday I need to take some time in class and sort of explain the topic, and then we'll implement it. Computing deflections is a straightforward operation, but explaining the background behind it takes a little bit of time. And I'd rather explain it, let it seep in, and then let's use it, okay? Because that method, we're gonna be using that method for beams later this semester. So it's a really important topic to cover. Okay, did I get the code? Okay, just so I'm pretty sure I went through this because I heard before class the familiar discussion around this time of the semester when students start talking about celebrations of learning. I wanted to make sure that we were all crystal clear as to when our first exam was going to be. And our first exam is going to be Monday, September 23rd. Okay, so let me zoom in a little bit. Like I said, we've been following our schedule pretty closely. So today is Wednesday, September 11th. We're discussing the method of sections today. Then Friday and Monday are going to be on deflections. So this day I'm going to talk about the background ideas, and then we're going to do an example in class on Monday. Wednesday, what I'm going to do is I'm going to introduce your project, your analysis project. Okay? Just just so you are aware, there are 2 submittals for the analysis project. One of them is due Monday, October 14th, but when you see how much work you have to do for that submittal, you'll realize it's very minimal. It's really not a lot of work. The bulk of the work for the project is during the submittal 2 phase, and submittal 2 is right before Thanksgiving break. The project will be open on Blackboard for a long time, so if you submit it early, that's fine. That Friday before Thanksgiving break, we're just going to sort of have a Q&A session in case anybody's having trouble with their project. Most students are able to complete it very easily, but if you're having any mask hand problems, that's usually what we're working out that day. And I'll have it collect by 5 p.m. Okay, but going back to more, local schedule, over the next couple weeks. So let me go over here. So we're going to be doing deflection and trusses Friday, Monday. We introduce the project on Wednesday. Friday, we have exam review, and we celebrate on Monday. Okay, and then after that exam, we get into shear and moment diagrams. So that's going to be our topic after the exam. Does that sound good? All right, any questions about schedule and where things are going moving forward? Everybody good? Sound good? All right, so our first exam is on Monday, September 23rd. All right, and everybody get the code? All right. Excuse me. All right, So we are going to be looking at the method of sections today. I've been talking about the method of sections quite a bit, but we haven't used it. I say we'll explore this one later. It's now later. We still are dealing with the same assumptions in truss analyses. You know, the idea that all the members are connected by frictionless joints, all the loads and reactions are applied directly to the joints, and the centroids of all the members coincide at the point where the joint is. So what that means is that every member is an axial force member. Now, let me go back and say one thing. When we did the method of joints, we were limited to joints with two unknowns. Why were we limited to joints with two unknowns? Why is that?
We only have two equations.
We only have two equations of equilibrium. But let's go a step further. Why do we only have two equations of equilibrium? Well, we have two equations of equilibrium because all the forces all meet at a common point. If all the forces all go through a common point, there's no moment, right? Remember, if you have a point, a moment is generated about that point when there's a force where its line of action is some distance away from that point, right? If you have a point and you have a force, the moment generated by that force is the magnitude of the force times the shortest distance from the line of action. So if the line of action goes through the point, there is no moment, right? That's not the case with the method of sections. With the method of sections, you're going to have forces going all over the place, okay? So the added advantage of the method of sections is that you are afforded another equation of equilibrium. So whenever you apply the method of sections, you can cut a section through at most 3 unknown members, right? So if you to be clear, you could cut a section through like 5 members, that's fine. But if you just wanted to apply the equations of status, you have to know 2 of the members beforehand, okay? The method of sections will allow you to solve for 3 unknown members because you have an added equation of equilibrium. Does that make sense? Now, let's talk about when to apply the method of sections because I focus, as a structural engineering professor, I focus my educational efforts for you all on the method of joints, okay? And my reasoning for that is that when you're a structural engineer trying to design a system, you need the forces in every member, okay? You need the forces in every tension member, every compression member. You need to know what's going on in the entire truss because you ultimately need to size the whole thing. So the method of joints, while tedious, it is, I think everybody would agree, it is thorough. It will give you the whole solution, okay? The method of sections is not really intended to do that. The method of sections is important if you only desire the forces in a couple members, okay? Now there are a few practical applications when that would be important. For example, if you're spot checking your calculations and you just want to make sure that you're getting the right force in this member, maybe it's easier to just cut a section as opposed to solving the whole truss. If you're trying to check another engineer's calculations, I'm sure by now you've heard that engineering calculations must be able to withstand the scrutiny of an independent review. The idea is that if I take your calculations and give them to my buddy Jerry Elkins is a bridge engineer that I know quite well. If I give him your calculations, he needs to know what's going on, right? And he needs to be able to check your calculations. You know, and it is that independent review that all design offices will do in order to ensure that designs comport with standards and specifications. So if you're just trying to spot check some things, method of sections works great. And you all are students. You all have an exam coming up next year, hopefully. Y'all know what I'm talking about? 2 letters, the FE, right? I guarantee you a very classical problem on the FE exam is, here's a truss, what's the force in this member? And it is often faster to solve for the force in that member using the method of sections, not the method of joints. Not saying either one won't work, but it is a test with a clock, you know? So let's just be honest with that. Okay. One question that I do get at this point is, well, Dr. Mike, hold on. You give tests too. Are you going to tell us which method? Maybe I will. Maybe I won't. But I also would expect you to maybe be engineers about it. Let me give you an example. If I were to give you this truss and ask you to tell me the force in member AF, what are you going to do? Probably method of join since it's right here. What if I told you the force in member CD? Probably section since it's faster. Do you see what I mean? So right off the bat, I'm asking you, if you ask me, well, are you going to tell me which method? I go, no, but it's not exactly an impossible puzzle to figure out which method you should employ. Do you see what I mean? Like, you can reason your way through which method you should employ for a given problem. Okay? Does that make sense? So again, I'm going to challenge you where it makes sense, but I'm going to challenge. But I think you can meet the challenge. I wouldn't do it if I didn't. All right. Excuse me. Now, one thing about the method of sections that needs to be clear is that the truss doesn't care which direction that you look. Okay. Do you remember when we were solving for reactions for beams that had internal hinges? And you would break out the whole samurai sword or lightsaber, and we said you could look at this side of the table or this side of the table, it doesn't really matter, right? The answer is the answer, right? It's not going to change dependent upon what section of the section cut that you look, or what side of the section cut that you look at. Same thing's true here, but that doesn't mean you need to make your life more difficult. For example, if I cut this section right here, I think everybody would agree it's probably easier to look at this side of the section cut than it is this, just because there's a lot more stuff going on. And if I'm being honest, there's a lazy aspect to it too, because if you cut a section, you typically want to draw everything that's on the section cut over again. There's a lot less to draw over here than there is to draw over there. This may be one of those areas where you can let your internal laziness meter guide you on which is the best way of doing the problem. I mean, the more steps that you introduce into your calculations, the more opportunity there is for mistakes in those calculations. You know what I mean? There's nothing wrong with taking a problem and making it easier. Okay? Excuse me. All right. Everybody okay with this? Okay. So I want to do this example. This is the method of sections example we're going to do. Let me pull up the notebook so I can prevent all the screen changing and whatnot. Let me make this a little bit bigger. Okay. Now what we're going to do is we're going to determine the forces in three members. I'm identifying three members, and we're going to determine the forces in those members utilizing the method of sections. So first off, let me break out my highlighter and let's... What's up? Okay. Oh, okay. That's fine. If you need to, that's actually not a bad idea because this is a big truss. So if you want to turn your notebook sideways, that's fine. Let me meet. Oh, I hope my voice didn't come out muffled over the past 10 minutes because I had my notebook over the microphone. So, apologies to the YouTube audience and whatnot. I blame Raid Shadow Legends. So, please don't sue me, Raid Shadow Legends. That was a joke. No, it's not. Video is sponsored by HelloFresh. No, okay. All right. So we're going to highlight the three members that we're going to solve for, which are CD, CK, and JK. Okay, we're going to highlight those members. So I think it's not a leap to suggest that when we break out the samurai sword or lightsaber, this is going to be our section cut, okay? And typically what I will do is something like that. So I'm calling this section 1-1, okay? If you want to break out some engineering 102 lingo, you could probably say I'm going to cut a section and look a certain way. What I'll probably do is look this way, simply because I don't really think there's an analytical reason for looking one way versus another. I mean, I've got two loads reaction, but it just seems like there's less to draw this way. So I'm going to look this way. So I'm going to cut a section and look to the left. And unfortunately, and again, this is probably the thing about the method of sections that students enjoy the least, is that you just kind of have to draw stuff over again. And let me be clear, you don't have to. But when you're first doing this, I'm telling you that I have, as somebody who grades these problems, have found a pretty direct correlation between students who do well on these problems and students who take the time to draw everything out. The ones who make mistakes are the ones who say, I don't need to redraw it, and then they forget an arrow or they forget a direction. So go through the process. All right. So what we're going to do is we're going to, section 1-1, and we're going to look left. Excuse me. Okay. So let me see what I can do here. All right. So I'm going to try and keep my calculations as neat as possible. All right. Or my sketch, not my calculation, my sketch. I'm going to try and keep my sketch as neat as possible. All right. Okay. So we'll do something like this. And let me show you how I'm going to draw this. I'm going to say, okay. All right. So what I'm going to do out here is I'm going to say like this. So do you kind of see what I'm doing here? Like we're cutting the section through these members, but I'm sort of showing you what the truss looks like out here. So I'm sort of using those dashed lines just to say we are samurai sorting or lightsabering through here and looking at this way, but this is just a sketch of what the truss looks like on this end. Okay? The next thing I'm going to do is that, okay, and that came directly from the problem. It's at a 1-to-1, that's at a 1-to-6. All right. See if we can put some forces to this. We have that. Notice how the reactions are not equal. Like this is 45 and this is 55, and that's because the loads are different. This is 20 and 20, that's 30 and 30. So if we were to apply a method of joints or method of sections analysis, we would need to solve the entire system, right? We could not solve just a little bit of it, right? So something to keep in mind. Excuse me. All right, so now let's start labeling dimensions. Let's do that now before we forget. Okay, so this dimension, this dimension, this dimension, and this dimension are all 30 feet. Okay. This dimension here is also 30 feet. Okay. This is also 30 feet. And if you'll permit me, I'm going to scooch this over a little bit. There's a reason why. Bless you. That's also 30 feet. And, oh, I didn't put labels. Let's put labels here. So this is A, I, J. This is joint K, B, C, and that's D. The joint labels there. We also need to indicate that this is 15 feet. And that's 10 feet. Okay. Did I get everything right? Any of my dimensions incorrect? I haven't put my unknowns on there yet, have I? I haven't done that yet. So we need to do that. But so far, so good. Is my truss drawn accurately? Okay. Or my section cut, I should say, not because that's not the whole truss, that's only part of the truss. Okay. All right. So now I'm going to put my unknowns, and I'm going to do something. I'm going to assume that all the members are in tension, okay? And I'm just going to do that just to make my life a little easier on the math, because I assume that they are all in tension. Any negative answers will be in compression, okay? Because I'm going to have a lot of unknowns. So let's just deal with that now. Okay. So I'm going to have member CD. Again, I'm assuming it's in tension because here's the section cut yanking away, right? Everything over here doesn't exist. Okay, the actual structure is over here. Okay, I'm just drawing this here so I have a point of reference. Okay, does that make sense? All right, so we're going to do a cut like this. Or sorry, a section like that. CKX and CKY. Again, note that they're at a 1-to-1. And then we're going to do JKX and JKY. Okay. All right. I know I did a lot of drawing, so I'm actually just going to take a second, let everybody catch up, see if anybody has any, get to this point, and see if anybody has any questions. So I'll give everybody a second. How are we doing? So far, so good? Any questions on the sketch so far? Okay. Now, let's start right now. Let's just start treating this like it is a joint analysis. Okay? What would happen if I sum forces in the x direction? How many unknowns do I have? In the x direction? This, and then these two components, right? How about in the y direction? Two. So applying the sum of forces in the x direction or the sum of forces in the y direction right now isn't really going to help, right? That should make sense. I mean, the whole point of cutting a section is to afford you the third equation of equilibrium. So if you cut a section and then you say, well, I'll sum forces in the x direction first and sum forces in the y direction first, that doesn't really make sense, right? We should be summing moments first. That was the whole reason for cutting the section in the first place, so that we had that tool available to us. So we can sum moments, okay? Now my question for you is where to sum moments, okay? Now before we start going into where to sum moments, I do want to make sure that we are all remembering this, the principle of transmissibility, okay? And so all that means is that if I have some line of action out in space and I have a force vector right here, I can take that force vector and move it along that same line of action And so if I'm like considering like this point right here, I could place that force vector here, 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 here. It doesn't matter, and I will still get the same moment about this point because the moment is calculated as the force times that distance there, right? So it doesn't matter where I place the force, okay? That's sort of the reason for drawing these dashed lines, right? Because I could do the same thing with the x and y components. I could take the x and y components and put it anywhere along that line of action, and I would generate the same amount of moment about that point. Because again, the moment about that point is the magnitude of the force times that distance. Okay? Does that make sense? Okay. So that being said, I guess we're all in agreement that we need to sum moments. Okay? So my question for the class is, where do we sum moments? Instead of picking the point, let's identify all possible points. So remember, we want to sum moments about a point that will eliminate as many unknowns as possible. Okay? So somebody give me a point that we could sum moments about. K. Okay, so that's one point. Okay, so let's write down K. Why did you pick K?
Because JK and CK both directed to K.
There you go. So if we summed moments about point K, we would isolate CD. Okay, that is an answer. Okay, but we could go about that. I'm gonna. There are some better points, but that is not a bad point. Okay. All right. Somebody give it another one. What's another point?
C.
C. C is a very possible answer. The structure does not care where we sum moments. It does not. Hill of beans, doesn't matter. Summing moments at C eliminates this diagonal and this, and we isolate that. That works too. There is a third point, by the way. Third point is what I will call point X. And that's this point right here. The point at which this and that cross. We could sum moments right there and get rid of this and that diagonal, right? It would work, wouldn't it? And that would solve for this one, right? So there are three, okay? So we'll call this X. All right, so let's talk about this. Hold on. All right, so these are my 3 points, and they each have a reason behind them. Okay, so eliminates CK and JK. Okay. Now, let's see if we can reason through, of these 3, which one should we go with? All right. Let's talk about point K, okay? Because that was the first one that was brought up. Let's talk about point K, okay? So let's sort of treat our equations of equilibrium like they're playing cards. Okay, so sum of forces in the x direction, sum of forces in the y direction, sum of moments, right? So let's talk about point K, because that was the first one that came up. Let's talk about point K. So let's say that I play that card. What is that going to give me if I play the joint K card? It's going to give me CD, okay? So I've used that, okay? And now I have member CD, okay? Okay, now what? Now I've got sum of forces in the x direction, sum of forces in the y direction. But how many unknowns do I now have in the x direction? How many unknowns do I have in the y direction? So is joint K really the one I should use? No, okay? So joint K is going to get a very scientific classification of a frowny face, okay? It'll work, but it's going to be, I'm going to have to break out my 2x2 equation solver. You know what I mean? It's just going to be more hassle than it's worth. Am I going to have that problem with joint C? Let's think about what happens with joint C. So what happens with joint C? If I sum moments here, I'm going to get member JK, right? And then once I get member JK, what am I going to be left with? 2 horizontals, 1 vertical. So then I can apply sum of verticals to get this slope ratio, then sum of horizontals, right? So that means that joint C gets the equally scientific classification of a happy face, okay? Now, as for point X, I'm going to give it a meh classification. And the reason why is because point X will also work as easily as joint C will, but in order to sum moments at point X, I am going to have to do a separate evaluation and figure out what that distance is. And I don't have to do that with C. You see what I mean? I know where C is. So in terms of where should we sum moments, I'm going to say we sum moments at C. Does that make sense? Didn't think emojis would show up in a in engineering calculations, did you? Is that the meh or should it?
No, man, that's good.
Is that good? Okay. Didn't think an engineering professor would ask that either, would you? Did you? Okay. So my smiley face looks like devious almost. I don't think. Okay. Okay. All right. Everybody good? Okay, so let's sum moments at C. Let's see what happens. All right, so summing moments at C. Do I need to consider this reaction? Yes.
Oh, wait, okay.
This one right here. 45 kips at a moment arm of 60 over here, right? What about this 20 kips? Okay. Do I have to consider this 20 kips?
No.
What about CD?
No.
What about CKY? What about CKX? Because the line of action goes through point C. So, okay. So we've got JKX and JKY. Okay, so let me sort of draw this here on the board. So here's point C. We've got member here like that. Then we've got point J, and we've got this line of action, and we've got this horizontal and vertical component, right? And we can put that horizontal and vertical component anywhere along that line of action. What I'm going to do is stick it right here. Why am I sticking it right there? So the vertical component goes right through it. Do I need to consider the vertical component? The only thing I need to consider is the horizontal component. So in other words, basically what I'm doing is I'm taking this and I'm moving it right there. So the vertical component goes right through, and then JKX has a moment arm of 25 feet. So I'm going to undo that. But you see what I mean? Does everybody see that? So therefore, $45 times 60, I think I can do that one for you. That's 2,700. It's 20 times 30. Oh, that's foot kips. That's 600. So here's what's going to happen. We're going to get that. Now, how did I get that it's going to the left? Well, originally on my free body diagram, I had it going to the right, didn't I? And I got a negative number, right? Because 2,700 over here, 600 minus 2,700 is negative 2,100. Ooh, sinus infection. And then divide out, get 84. What do we think? Does that make sense? Okay. At this point, I am hoping that the problem is now pretty rote. So tell me what to do if I have JKX. Slope ratio to get JKY, right? So if I look at JKX and JKY, how am I going to get JKY? Is JKY 6 times that of JKX, or is it 1/6 of JKX? 1/6. The vertical component's tiny, right? So therefore, slope ratio and 84 times 1/6 is 14. But that's going down. And it's going down because my assumption was incorrect about JKX. It's going to be wrong about JKY as well, right? So if you want, you can think of this as, if you want, you can think of it as negative 14 kips or 14 kips down. All right. How are we doing so far? Okay. So I want you all to tell me what to do. Tell me what to do. What's that? Well, do we need to do a joint analysis at all? I'm saying we have JKX and JKY, so what do we do? What's that? Some forces in the Y direction. So, give me 1 second. That's going to bug me. Okay. We're going to sum forces in the Y direction. So my apologies for the scrolling up and down. So I'm going to do some scratch calculations here on the board so that I don't have to scroll up and down too much. So what do I have? I have 45 going up, 20 and 20 going down. So what about CKY? I have that going up? Yes. CKY is going up. And then JKY is going down, right? I have it going up here on my sketch, but I found out that it's going down. So you can handle that one of two ways. You could say that JKY is negative 14 up, or you could say it's positive 14 down. It doesn't really matter, just as long as you're consistent. So we'll do it like this. We'll do it like that. We'll say JKY is 14 down. Okay. So that's going to be my summation, right? So let me put that here. I'm going to put it in my notes a lot more neatly than I have here on the board. I just needed something to sort of go off of. So I got 45 CK Y going up. Got that going down. So 20 and 20 is 40, 14, 54. So that's positive 9. So positive 9 means 9 kips going up because we assumed it was going up and we got a positive answer. If CKY is 9, what is CKX? 9 because it's at a 1-to-1 slope ratio. Okay. And so now we can sum forces in the x direction. My apologies if my calculations are a little more scattered. I'm just trying to keep everything on the board as effectively as possible. So I'm going to do my little board trick one more time. So what do I have horizontal? I only have 3 forces horizontal. They're all the unknowns, right? I have CD to the right. I have CKX. What was CKX? It was 9 kips to the right. And what about JK? What was JK? 84 to the left. So that's going to be my summation. So therefore, no, you're fine. We're doing good. Everybody good on this? Okay, so if we summarize, just to summarize what we've got going on for the problem. First off, so if we do these, because we've got to use Pythagorean theorem on both this and JK. So 9 squared plus 9 squared is 9 square root of 2. And what is that? And then JK is
85.16.
so therefore CD. So CD is 75 kips. CK is 12.73 kips. I can be neater than that. That 3. Last thing to do is figure out our tensions and compressions. What member is CD? Is it tension or compression? Tension, CK, and JK.
Compression.
There we go. So tension, tension, compression. Boom. So what do we think? What's that? Fire, is that what you said? Fire emoji? Yeah. Should just start putting emojis after every problem.
Put him in the blackboard.
Do you want me to put? Hold on. How about this? Hold on.
Let's see the emoji.
Let's see when we do that.
Reed's gonna love that.
What's that?
I said Reed's gonna love that.
Wade's gonna love that. Then I put hands in no tap. He doesn't. Does he like no cap? What is he? Is he fine with cap or no cap? I'm such a dork. I know. All right. I'm going to pull up the QR code one more time, but that's all I got, everybody. Friday's going to be an interesting lecture, so I'll see you then.